before we really start with the new stuff, what we have been looking at yesterday in the context of this one-dimensional P-wave superconductors. So remember, this was the Hamiltonian that we introduced. It was a one-dimensional system of spinless fermions with tunneling, pairing, and a chemical potential. And by just tweaking a bit the parameters, we have seen that there are at least two representative phases, one where the chemical potential is different from zero, and instead the pairing and the tunneling are zero. And we draw a cartoon for this phase after introducing these Majorana operators. And the cartoon of this phase was that this Majorana operator just pair on each side. And this phase was trivial, obviously, because it was just a phase with no particles. And then we have also seen that instead, if you do the opposite, so put the chemical potential to zero, and put the tunneling equal to the pairing, what you see is that instead of pairing on every single side, the Majoranas actually pair in a completely different way, and they actually do pair off-site. They create this nearest neighbor connection. And what is very important is that if we have a system with open boundary condition, we have this decoupled zero energy mode. Okay? So this is where we arrived, and in principle, this phase, when we close it, has also a bulk gap over the T. So we can make the system that this might be stable, but now we want to prove it, yeah? Because as was said by some of you, I mean, this is, if you want, immense fine-tuning. Okay, is this really a stable phase of matter, or is everything washed out once we change a bit these parameters and so on and so forth? So the first part, we will actually study the phase diagram of the model. Then we will gain insight on why this phase is topological by establishing a correspondence between the Kitaev model and the Ising model. Okay, let me call it HK for simplicity. H-Ising. And maybe some of you have already done it yesterday, and we will understand what are the similarities and what are really the differences between these two objects. And this will allow us to make some statements about phenomena which are related to Josephson effects, for instance, so they can really be measured. And then at the very end, I will discuss what can be potential ways to actually observe Majorana physics, Majorana zero modes. M is Majorana zero modes in cold atoms. A bit like what we have done yesterday for the Haldane phase. Before I actually start with the new stuff, are there questions about what we did yesterday? Okay. No? So we start. Phase diagram. Now, the phase diagram of this stuff, of this Hamiltonian, you can immediately guess that this is particularly simple. And the reason is that this is just a quadratic Hamilton operator. So we can try to even exactly diagonalize it. Okay, so what we do, we assume now periodic boundary conditions, so that we use k-space operators. So AK, this would be 1 over the square root of L, sum over all the possible. Actually, we want to have an expression of AJ as a function of AK, sorry. So K in the Brillouin zone, e to the I kj times AK. Okay? We just go to momentum space, and we rewrite this Hamiltonian in momentum space. Okay? You can take a 1 over L in front. Since everything here contains two operators, you will have a sum outside over all the possible K's and Q's that span over all the Brillouin zone. Actually, let me also write it, Brillouin zone. And then we can start applying our formulas. I mean, the first operator is a dagger. Then we have a sum here over all the possible J's. And this will be a dagger k a j e to the I k, sorry, this is a q, yes, k minus q times j. But in addition, since this was j plus 1 or I plus 1, we have some remaining factor here, minus q there, okay? Plus the emission conjugate. Okay. The second term, I mean, can be done in exactly the same fashion. This would be a sum over j. The only difference here is that we will have a dagger k, a dagger q, and this also implies that in this exponential, instead of having k minus q, we will have k plus q times j e to the I q plus admission conjugate. Okay? Yes? You have a question? Sorry, can you? T? Sorry, T and W. You're right. I was missing them. And then there is obviously the chemical potential. This would be sum over all the possible j's, and this is particularly simple because what we have here is a dagger k, a q, e to the I q minus k minus q, q times j. Okay, it's a very conventional. If some of you have already seen Bogoliubov solutions, you already know very well how to do this calculation. Okay. So now the key feature is that you can recognize here that there are a lot of delta functions. Okay. Whenever there is a sum of j, you see everything here is independent of j apart from this phase factor. This is the only place where j actually appears, also here and also here. So this is a lot of delta functions. We just solve them, and they also reabsorb the L. They cancel the sum in j, and they leave us with the sum over all the possible k in the Brillouin zone. Okay. We just have to be careful what are the type of delta functions that we have. I mean, this is a delta function where k equal to q. This is k equal to q, but this one is actually k equal to minus q. Okay? Which is natural, because if we have periodic boundary condition, this means that we want to conserve momentum. So if there is a tunneling, obviously is a dagger q, a minus q. But if you have pairing, you want to create and destroy resonant pairs, they cannot happen at k and k again. They have to happen at k and minus k to conserve momentum. Okay? So we just write it up, and this is then minus t. Oh, sorry, there was also a minus. Okay. And then the first term is a dagger q, well, a dagger k, a k. But remember that there is this stuff now. E to the minus k plus admission conjugate. Then we have the second term. Okay. We will have a dagger k, a dagger minus k, q is equal to minus k, e to the minus I k plus admission conjugate. And then the chemical potential instead gets essentially no k dependence, as it should be. And this is just a dagger k, a k with a mu in front. Okay? Erase this part. Now, if we want to solve it, the Bogoliubov de Gennes, I mean, what is typically done, if you don't have particle number conservation, this is the case also here, you want to decouple your Hamiltonian into positive and negative momenta, okay? And then just do the conventional Bogoliubov stuff. Let me skip this. I just tell you what the final result is. I mean, you define spinors psi of k. Let me actually define the dagger. This is nothing but a dagger k, a minus k. Okay. And if you rewrite your Hamiltonian now, in matrix representation as a function of this psi's, this becomes something like this. This becomes the sum over all the possible k which are larger than 0, okay? Because we want to reabsorb the negative ones into the sum in a compact fashion. Then you have this spinor. Then you have a matrix here, A of k, okay, and then this A of k, which is really the important stuff for us, as the following form, okay? So here we have, the chemical potential, you immediately see where it is, okay? This has to be always on the diagonal, it gets no k dependence. And then we have minus 2 t cos k. This is the single particle stuff. Here we also have the chemical potential, but as opposite sign, because we are actually just taking this A minus k into the dagger, so there is a minus 1 coming from an anti-commutation relation. There is nothing specific. And also the other guy changes sign, t cos k. What is actually and this is the typical stuff that you also have when you have just free fermions hopping on a lattice, okay? Actually, for free fermions, you don't even have to write everything into this form. You know what the dispersion relation is, and then you have solved the problem. Now, the funky thing is that this pairing operator, this is the only operator that can actually appear outside of the diagonal, and it does. And what you get is that this is actually 2i sinus of k times w. And this is minus 2i sinus of k times w. Now, the spectrum of the theory is nothing but the diagonalization of this matrix. Okay, so we can do it very quickly. And you notice that this is nothing but minus the other one. So if you write the eigenvalues equation, they will be in the form lambda minus alpha times lambda plus alpha. So this is lambda square minus alpha square minus beta square. So this means that lambda plus minus, so epsilon plus minus, is equal to the square root of this guy squared. So this would be 4 sine k. Yes, there is a minus here, so it compensates the I. Let me write it properly. Sinus square of k times omega square. And then we have plus this other term, which is mu plus 2 cos k times t, square. There's also a mistake here. Yeah. So this is our dispersion relation. Yes. Yes. Now, when we want to determine a phase diagram, what is the rough way of determining it is to determine what are the critical lines or critical regions. So we want to understand as a function of the parameters of this Hamiltonian where we have something which has no gap. Okay? But that's easy. Okay? There are not many ways you cannot have the only way you can have a gapless region is that if this one and this one are at 0 at the same time. Okay? There is no other way of having something which is a gapless dispersion relation, right? So we identify two things. The first one, when both of them are 0, this implies that either we have W equal to 0, so we don't have to wonder about this guy. Then the problem is like free fermions, and free fermions, we know, they are gapless as long as the chemical potential is within the bandwidth. So whenever mu in absolute value is smaller than 2t, then it's gapless. And you can easily remember, this is the dispersion relation of free fermions. You put the chemical potential somewhere, obviously you're gapless. Okay. This is one regime where this is gapless, but then the other regime is also possible when this one is 0 despite the fact that omega is positive. So this implies that k is equal to 0. Let's put this in parentheses. So W is different from 0. But then if this guy is 0 because of k fine-tuning, this implies that when k is equal to 0, so this cosine is 1, the only way we can actually make this 0 is to define mu equal to plus t. plus 2t. Obviously, we can make this 0 also by going to pi, right? This changes the sign of the cosine, and then we have mu equal to minus 2t. Okay? This is trivial. If you have one, you must have the other. Now, let's now draw the phase diagram according to these simple conclusions. And typically, the phase diagram of the model is, we have to fix one energy scale, so we put here mu over t, and we put here delta over t. Okay? Now, let me use colors. Okay. So this is clearly a line, okay? Is w equal to 0. So, not delta, this is w, sorry. Okay? So this line is gapless. It's gapless as long as mu in absolute value is smaller than 2t, okay? And we know also along this line what the theory will be. This will just be free fermions, okay? So it's not very interesting, yeah? Free fermions. Now, these are the two lines. They actually are instead vertical in our case, and they are done like this. Okay? So this is our phase diagram. What is the only thing that we could have missed? If there was a first-order transition, because first-order transitions are not signaled by any gap going to 0. Okay? But I tell you, trust me, they are not. There are no first-order transitions. Okay? You can check it by looking at the fact that the energy doesn't have a discontinuity. Now, remember that yesterday we studied these 2 points. One point was when t and w are 0, and mu was finite. That was the trivial phase. Unfortunately, it's a bit hard to see a point where t and w are 0 since t is here. So this point was kind of a strong coupling here. This was a very large W. So essentially this is telling us that this region is trivial. Because this is the region where there are no particles. And the opposite is also true here. This region is trivial, here instead there are particles everywhere. Okay? What was the other point that we studied? Mu equal to 0 and W equal to T. So the other point that we studied was actually this one. Now I'm running out of colors. Let me try to use the yellow. Okay? So this one is very far from any transition line. So out of this simple calculation, we can immediately conclude that the very fine-tuned point that we were looking at yesterday is actually representative of a full phase. Okay, so it's something whose properties are to some extent stable. Yeah? That's an important statement. Yes, I mean, the problem is the following. If I give you a very fine-tuned wave function, and I tell you I want to conclude properties of a system based on this wave function, then the next thing that you should tell me is if this wave function is really representative of a phase, or is, for instance, if you were sitting at a very peculiar point in a phase diagram. Okay? Either if there was crossing of phase transition, or because there is an enhanced symmetry, or something like this. Out of this calculation, you can conclude that these scenarios are not happening. Your representative wave function that we studied yesterday, representative fine-tuned point, is actually within a phase, so it's representative of a phase. If you look at the properties of the system, like the presence of these edge modes, they will appear everywhere, okay? As long as you don't cross a phase transition. Like? Sorry? Exclude BKT. Actually, even within BKT, which kind of phase transition are you aware of? First order, second order, if you want infinite order, okay? If it's second order or below, what happens? The spectrum has to be gapless, okay? And I've shown you that if the spectrum is gapless, the only thing you can do is to either be in scenario 1 or scenario 2. Then you can tell me, and this was what I was mentioning, but maybe you missed a first order transition, okay? I've not shown you. What is the simple, if I tell you the spectrum, what is the simple way of saying if you are in a first order, if you are crossing a first order phase transition? If the spectrum is discontinuous. Yeah. And this is not, clearly. I hope I don't have to prove it. Okay? Okay? So, in this sense, you are completely sure about the statement that I've just made. I mean, it's not a very strong statement, it's single particle physics, yeah? Okay. Mm-hmm. Okay. And not of a phase and not of a state. Okay. Then you have to think about what is, I mean, what is the feature, the specific feature of this state, which instead will not be present in the full phase. And what is the specific feature? The specific feature is that the correlation length of the state that I just draw was essentially 1. So there was no correlation beyond one side, because it was almost a product state, right? This will not be true, because we know that at the transition line, the correlation length has to be infinite. Okay? Here, if it's order 1, correlation length, okay, of order 1. Here is infinite, so this correlation length has to change. Okay? What does it mean physically? Okay, let me take again the simple picture that I had, God bless you, okay, of these singlets, paired Majoranas, and these edge modes. Whenever you move away from this soft spot, obviously this is not exact ground state anymore, but you have to imagine that the wave function of this object extends a bit in the bulk. Okay, if the system has no bulk gap, the extension can be power law. However, this system has a bulk gap, because we have seen that you can write each of these pairs as essentially as a free Fermion harmonic oscillator, a dagger A, this A tildes, right? So every time we try to leak this wave function into the bulk, we pay a cost, energy cost, which is of order W. This means that the best this guy can do in perturbation theory is to move a bit and then come back. And then this means that the extent of this stuff has to be exponential, okay? Because if he tries to move further, he has to pay a lot of, okay? So already by just simple perturbation theory, you can wonder that you will have a wave function of this Majorana mode, or zero energy mode, which extends into the bulk with a kind of correlation length prime. Actually, this correlation length prime doesn't have to be exactly the correlation length of the bulk. Okay? There are reasons for that, which I don't want to enter into, but they are typically correlated. Okay? Also because they depend on similar energy scales. Okay, so this is the phase diagram. We have made our statement. We know about this exponential scale, but then, so please. That's correct. That's correct. Okay, okay. Mm-hmm. Okay, you are essentially asking me the following. I told you the phase diagram of a system, and in order to derive the spectrum, I used periodic boundary conditions. So the only thing I was sensitive to were bulk properties. I was not sensitive to edge properties as of now, right? However, if you have a system which is defined on open, you imagine that the bulk gap does not change. Okay? So what I've shown you here is that the system with open, this is a definition of a bulk gap. It does not change with boundary condition. Do you agree on this? Otherwise, it's not a bulk gap, right? Otherwise, okay. Okay? No, I mean, this has to be like this. Okay, the bulk gap does not depend on boundary conditions. What I've shown you is that if you take these wave functions, okay, you can define here two kind of excitation, either an excitation in the bulk or an excitation at the edge. Okay? The excitation at the edge was this A tilde L, and everything else was in the bulk. Okay? So if you want, your bulk wave function was defined by the property that it's annihilated by any of these A tilde j, as long as j is in the interval 0 to L minus 1. Okay? You cannot excite, you pay an energy cost to excite each of these Majorana modes. Okay? Now, essentially, I've told you already that this is sufficient to show that the edge modes are stable. The reason is the following, is that if they were not stable, this means that you have at least 1 degree of freedom that introduces in the Hamiltonian a term that couples the first Majorana to the last one. Okay? But this term is exponentially suppressed if I have a bulk gap, right? So that's the reason why you don't see that. Out of this simple analysis, you can also guess that there might be finite size effects. Because, for instance, if I take a system with open boundary and it's too tiny, a term of this type, it's true that this is exponentially generated. But if the system size is too small, you will have the two Majoranas talking to each other. Okay? So this means that you will lose the property of them being edge modes, because they will then leak into the bulk, because the system is too small. Okay. Other questions? No questions? Okay. So we have made this statement, but I mean, as of now, the only thing which I really told you was related to topology is the presence of these edge modes. I've not shown you anything else which is related to topology. And now we do it, and we do it by doing the exercise that maybe some of you have done at home. So studying the relationship between the Kitaev chain and the Ising model. Okay? And the stuff that I will be telling you now, it's obviously fine-tuned in the sense that the formulas that are only useful for this model, but it's extremely useful also for other topological models if you will encounter them in the future. Okay? So trying to relate something which is topological and something which we do know it's not topological at all. Okay? So Kitaev, Ising. No. We start our exercise by taking the system with open boundary conditions. Okay? And then we say, okay, we can apply what is called Jordan-Wigner transformation. Jordan-Wigner transformation is a one-to-one mapping, highly nonlinear, between fermions and spins, and essentially, let me fix the notation here. Okay. Instead of the fermionic number operator, we use a spin, a Zj. Okay. So this is describing us the correspondence at the level of Hilbert spaces. The fermions, they have the state 0 and the state 1. And the spins have the state down and the state up. Okay? In addition, there must be an operator correspondence, and the operator correspondence is also quite simple. So if you want to have sigma plus j, this is equal to the products L from 1 to j minus 1 of 1 minus 2 and L a dagger j. Okay? And you can invert this. Okay? Why do we need this object? Well, the other reason why we need this object, which is called Jordan-Wigner string, is to ensure that we have the proper commutation relations. Okay? This is the only thing that this object really does. And you can easily check that if you plug this guy in, you get the right commutation relations for the spins and the right commutation relations for the fermions. Assuming that you have the right commutation relation for the fermions. Okay? Now, what happens to our Kitaev model now when we apply this transformation? Okay? Well, the chemical potential, we don't even have to guess what happens. This will just be sigma z plus rubbish, okay? So now we try to see what happens. And Ising side, when we go from the Kitaev to the Ising, the first term, which is faster, we write it is like this. Okay? We don't even have to think about it. Okay? But then there are the other two terms, the tunneling and the pairing. And both of them do contain the string in principle. However, you notice immediately that if I have terms which involve, for instance, fermions or nearest neighbors, what does happen? They are carrying twice the string until the site j. Then there is the e to the I pi and j or something, the parity, but this is automatically killed by this guy. It's a constant. So this means that I have no strings. Okay? Let me just write down the formulas, okay? This will be the product from L1 to J minus 1, 1 minus 2. Okay, I have to do the opposite stuff, so this will be sigma z, L. Then you have a sigma plus J. Then you have another string from L prime from 1 to J, sigma z L prime, sigma minus J plus 1. Okay. All the terms in this product, they cancel because sigma z square is 1, apart from the term at J. The term at J is actually multiplied later by sigma plus. So the only thing I can do gives a minus sign, because if it was a plus, I apply sigma plus is 0. Okay, so I can cancel this. Pick a minus sign in front. And I have this term. So the string completely cancels. Okay. This means that I will only have two body operators. Now let me take for simplicity t equal to w, otherwise it becomes an xy model is a bit longer to write. So if you take t equal to w, the only thing that you get at the very end is that here you have a w sum from j1 to L minus 1, sigma x j, sigma x j plus 1. Okay? So this exotic string that we were looking at is doing nothing. We have an identity between Hamiltonian operators. What does it mean? It means that if you look at their eigenvalues, they are the same. The spectrum is the same. But now, I just told you that before, in the Kitaev model, there was a twofold degeneracy due to the fact that this A dagger L was 0. So let me actually use this table. And here I put Kitaev, and here I put Ising. And here I put the system parameter where mu were larger than 0 and t equal to w equal to 0. And here I do the opposite, mu equal to 0, t equal to w. So what was our interpretation? I mean, this phase here was trivial in the Kitaev. And this phase instead was we think it's topological because we have seen the edge modes. Okay, edge modes. Edge modes means that under open boundary condition we have twofold degenerate spectrum, okay? Edge modes. Now, how does this correspond to Kitaev, to the Ising? Well, when I have mu larger than 0, t equal to w to 0, the Ising model is just the first term. That's a paramagnet. Okay? Which is somehow relieving us because it means that something trivial remains trivial. Okay? When W instead is different from 0 and mu is 0, in which phase are we in the Ising model? We are in the symmetry broken phase. Okay? Then it depends on the sign of the coupling, if it's ferro or anti-ferro. Let's suppose it's ferro, so the coupling here is negative. And now, what happens in spontaneous symmetry breaking? The symmetry that you break here is Z2. And how many ground states do you have when you break a symmetry which is Z2? 2. Okay. Okay. So everything seems to work fine. Okay. We have an equivalence under open boundary condition of the two spectra. This allows us to have a simple interpretation of the trivial phase, which we didn't need because it's already trivial. And it's telling us that, look, when you look at the topological phase here, this corresponds in the Ising language to something which has a symmetry broken phase. There is a problem though. What is the order parameter for this phase? Sorry? There are 3 magnetization. Which one? Sigma x. Okay? Here we encounter a problem. Sigma x in the Fermionic language is a non-local operator. So this means that necessarily there must be a non-local operator in this phase, which is actually our order parameter. This is your answer today. Okay? So this immediately tells us that on this side we require a non-local order parameter. This cannot be local. This is again open boundary condition. However, the biggest surprise comes when you start studying a system which is actually periodic. Okay? So before actually doing the formulas, we know already what happens on the Ising model side. On the Ising model side, if the system is open or periodic, do you really care? No. Because spontaneous symmetry breaking is always there. Having all ups and all downs, if the system is open or periodic, it makes no sense to change it. So the twofold degeneracy will remain also if I have a periodic boundary condition in the Ising model. However, in the Kitaev, we have seen yesterday, it looked like that if you close it, there are no gapless edge modes anymore, because there is coupling. Yeah? So is there something strange happening? Well, there is actually something strange. Yeah? And let us go back and look at what happens when we have a periodic system and we use the Jordan-Wigner. Okay? My periodic system is now a circle, and this is my site number 1 and the site number n. So at the level of Hamiltonian, there is only one term that changes from open to periodic. Okay? So the Hamiltonian of the Kitaev, for instance, under periodic, is the same of the Kitaev under open plus what? The coupling between these two sides. Okay? So there will be T A dagger 1 AL plus Hermitian conjugate plus W A dagger 1 A dagger L plus Hermitian conjugate. Okay? Now, this term has a peculiarity. That when we apply the Jordan-Wigner, what happens to the strings? It does not cancel, because there is only one. Okay? Let us actually write it. If I write A dagger 1, AL, well, A dagger 1, according to our mapping, is just sigma plus 1. Okay? But AL has all the strings, so this will have the product from K1 to L minus 1 of sigma Z K times sigma minus L. Okay? When we use closed, or in this case periodic boundary condition, the Hamiltonian is not local. Okay? However, it's not local in a very specific way. Okay? Because what is this operator? Well, it's almost like the parity. Almost. The only thing that is missing is the sigma z at the L site. But since it's sigma minus, the only non-trivial action is on a state which is up, right? And he puts it down. So what we can do here, we can put also the sigma z of the last site, and we just pay the price that we put a minus. Okay? That's just formal manipulation. It's an operator identity. You can just do it. But now, since this is the parity, we can try to move this parity, well, either on this side or on the other is the same. Typically what you do, you put it in front of this side. So what you have is sigma minus sigma plus sigma zl, minus sigma zl. Then you have the parity, but when you move the parity, you get a minus sign because you are encountering one operator, so you cancel this one. And you have something like this. Okay? Still non-local, but now it's in a much simpler fashion. Okay? It's the nearest neighbor term times the parity. So this means that when we close the system, the spectrum of the Kitaev chain, if the state has parity plus 1, is the same spectrum of the easy model, because this guy is just a plus 1. Okay? So now there are two cases. Okay, if I have the energy spectrum of the Kitaev model under periodic boundary conditions, this maps exactly to the spectrum of the easy model if I have periodic boundary condition under the assumption that the state has parity plus 1. However, if the state has parity minus 1, we get a sign here, and if I have a minus sign in the coupling between these two, am I doing periodic boundary conditions? No, I'm doing antiperiodic. This means that this is true for the parity plus 1, but its part which is actually parity minus 1, PBC. Minus 1. This maps into the easy model with parity minus 1 under antiperiodic boundary conditions. And here we are. Okay. Now, spectrum of the easy model, fix the parity. This is only one state. Is this state degenerate with the antiperiodic? No. Because when I change the boundary condition in the easy model, I'm putting in a domain wall. I cannot have all the bonds which have a same sign, right? There is one which has a minus sign. The way of minimizing the energy is to put a domain wall. This is correct. It's telling us that the Kitaev model under periodic doesn't have a degenerate spectrum. And actually, its energy gap, we can even write it down, its energy gap delta is the same energy gap of putting a domain wall in the easy model. Okay? Gap, domain wall. I think this is kind of shocking for some of you, so I will suggest that we take a short break and you digest this idea, because then we will do twisted boundary conditions, which is the next step, but it's very easy if you understand this. And we will discuss, in the last part, the connection of the findings that we have just seen to cold atom experiments. So I suggest that we reconvene at 12:15. Okay? Okay. Finish the lecture relatively quick so that we have time to have questions and discussions, since this afternoon unfortunately cannot stay. Okay, so for the sake of convenience, let me repeat this argument by just using drawings. And since I'm not Picasso, they will not be very, very good ones, but okay. So, the typical way you draw a spectrum of a many-body system is like this. Okay? You take the energy, you select the eigenvalues of symmetries that you are aware of. Let us take it simple, and then let's take the easy model. So the only eigenvalue is the Z2 parity. Okay? So this will be parity minus 1, and this is parity plus 1. Okay? And what I've told you is that if you have periodic boundary conditions, which I will use a color for, green, the spectrum of the easy model is exactly the same. So there are two almost degenerate ground states. With almost degenerate, I mean that at finite size, the splitting between the two is exponentially small. And then there are excitations. Blah, blah. We don't care. Okay? There's a gap. It's the same gap, actually. Spectrum is exactly degenerate. Instead, if you plot the spectrum with anti-periodic boundary condition, okay, the energy is not the same as with periodic, because I told you that when you look at the system which has anti-periodic coupling, you have to put at least one domain wall in the easy model. Okay, so this will be something like this. That. And actually the spectrum is gapless in that case. So this difference here is the energy of a single domain wall. Let me call it small delta in the easy model. Can you actually read can you see the red properly? Okay. Now, on the other side, now we do in the kit I have. Again, we have only two symmetries. Now I need two other colors. Okay. Periodic. Okay. Periodic, I've told you that for the eigenvalue of the parity plus 1, the spectrum of the Kitaev model is the same spectrum of the easy model. So I have to take this and put it there. However, for parity minus 1, I cannot take the spectrum of the easy model with periodic, but I have to take the spectrum of the easy model with anti-periodic. Okay, so this is the yellow one is Kitaev BBC. Let me also put labels in this picture here. This is PBC, and this one is APBC. Okay. Now we can make a last experiment, which I don't do it now. You can do it easily at home. So if you take instead the Kitaev model with anti-periodic boundary conditions, you actually will see the opposite. So that the parity minus 1 maps into the periodic minus 1. And the same happens, and the opposite happens here. Okay. So for the Kitaev model, the ground state actually changes its parity when we change the boundary conditions. Okay. In one case, with antiperiodic is at parity minus 1. In the other case, it's at parity plus 1. This phenomenon is also called parity switch. Parity because it's parity, switch because it's switch. So it's not a very... Okay. Now, actually, are there questions about this? It's important. No questions? Please. Yes. Yes. The duality transformation at the operator level is exact for periodic boundary condition only for the parity plus 1. For the parity minus 1, we have seen actually the Hamiltonian operator changes. Yeah? And the opposite is true for the antiperiodic. And the antiperiodic is true for the case parity minus 1. So no, it's always true for the parity plus 1, sorry. Okay? So in principle, the duality is always dependent on the eigenvalue of the parity for the Ising model. There are other dualities which are not like this. I mean, the Ising model has this funky property, is a self-dual. So you can map the Ising model into the Ising model. This is actually the easiest way of having an exact solution for its transition point. But that property does not depend on symmetries. There are other properties I was discussing with some of you during the break that are useful to understand two-dimensional system, two-dimensional topological order, like the duality between the Ising model and the Ising lattice gauge theory. This is also is actually not a one-to-one mapping, and also depends on other properties of the system, like boundary conditions, very heavily. Other questions? No? Okay, so a simple way of understanding this parity switch is actually the following. Because how do you do this in an experiment? Well, actually, switching an eigenvalue is not so easy. But what you can do, you can try to build systems of this type, where you put your wire in contact with two superconductors, one which has a certain phase θ1 and the other one has a certain phase θ2. In the middle there is no superconductivity, so this is trivial. Changing the relative phase between the superconductor is a bit like changing the boundary conditions of the system. Okay? Why it is so? In this setup, which is the realistic one, is not clear, but if I put it on a circle, you immediately understand that if I pierce a flux of magnetic field, in the system I'm changing the boundary conditions, obviously. And and piercing a flux of magnetic field is equivalent, to some extent, to changing the phase of the superconductor you're coupling to. Okay? There is a one-to-one relationship. Okay? But anyway, since this is it's actually a bit more complicated because there are also supercurrents, let's discuss the simplest case. So if you have something like this, let me put this angle theta. This is equivalent, having the difference θ1 minus θ2 is equivalent to put a boundary condition which is twisted with this angle. And this is theta. That's theta. And what you can easily verify, theta equal to 0 is obviously periodic. So you will have a state with parity +1 and a state with parity -1. You will have the same state for pi, because of this factor of 2. So I have a state here +1, state here -1. However, at antiperiodic, you will have the opposite. You will have a state, this is +1, this is -1. Here you will have the opposite, that the state here is at -1, and the state here is at +1. Okay? Because we have just demonstrated it there. Okay? And now, let me use yellow and violet. What you can do, analytically, because we can solve this model analytically, you can follow the path of these low line states for the parity +1 and for the parity -1. And see what the parity switch is. Okay? Adiabatically changing the phases of the superconductor. If you just put a phase which is 2 pi, you end up actually in a different state. Okay? Cross. Good point. This means that at this very specific point, the duality actually is exact for both periodic and antiperiodic. Okay? And this you can prove. It's a point which is actually a twisted boundary condition of pi over 2. Okay? And at that specific point, the Ising model for pi over 2 and 3 pi over 2 has the same spectrum. This means that the ground state is degenerate, and you will see it here because it's a crossing. The y-axis is the energy. Sorry, obviously it's the energy of the lowest state for each parity sector. Okay? Now, there are some caveats to what I've said, okay? Because this is true at this ultra sweet spot t equal to w. What happens when you move around? Actually, you see that you open small gaps here, okay? So these are not exact crossings anymore. because at whatever system size you have, the Majoranas talk a bit to each other. Okay? There is no way of making them perfectly isolated. Now, what happens if we do a Josephson experiment with this spectrum? Okay? If we move this angle, this phase theta, I mean, absolutely adiabatically, okay, we end up with a current which is 2 pi periodic, because now let us put a small Josephson walking on this path. If we go fully adiabatic, we actually do this. Okay? And so we have a system whose current, and actually whose energy, is 2 pi periodic. Okay? However, it's impossible to go fully adiabatically. I think we agree on this. So there is always a bit of Landau-Zener tunneling to highly excited states, and the Landau-Zener rate also depends on speed and so on and so forth. But let's suppose that we go at a reasonable steep with respect to all the energy scales here. Since here the adiabatic continuity is with the state here, so the derivative of this line, very close to this crossing point, is actually pushing us towards the other one. What really happens is that this small guy does not go there, but he populates an excited state because of Landau-Zener, okay? And the same stuff happens here. This means that if in an experiment you perform a Josephson measurement of the current, you don't see the spec effect here. You have 2 superconductors. You don't see the 2 pi dependence of the Josephson current, but they actually see a 4 pi. It's called 4 pi Josephson effect. At the very beginning of the Majorana in solid state, this was thought to be quite a strong evidence that you have Majorana edge modes. Unfortunately, this effect you can also have for other reasons, so it's not unambiguous, but it's very instructive in the sense that for us it tells us what is the important. We can read it off out of the importance of the boundary condition directly with respect to something that we can think about realizing in experiments, like pairing our wire to 2 different superconductors. Oh, this is just the definition. Okay, because when you take the definition of the phase of a superconductor, remember this comes with a dagger. So the pairs of these 2 phases is the real phase of the superconductor theta. That's why you get the 1/2 here. That's the only reason. Okay, you want to have something that upon a gauge transformation enters with theta on the boundary conditions, and since you have an a dagger in front of the superconductor W, you have something like this. You have W e to the I theta bar, right? Oh, blue is not useful, sorry. Yeah. W e to the I theta bar, and then you have a dagger, and you want to reabsorb this in the operator, that's why you get the factor of 2. Okay. So, how to observe this stuff in a cold atom experiment? First statement, this has never been observed in a cold atom experiment. Not yet, at least. Okay? So it's not so easy. And it's not so easy for many reasons. The first reason is that it's very hard to probe these Majoranas, and you can imagine why. I mean, these are modes which live at 0 energy. Okay? So this means that all your energies, you have to be very close to ground state physics to see them at all, otherwise you have temperature effects. They are also hard to detect, because imagine that you have a global probe, like a momentum distribution. This will most probably not be sensitive to an effect which is all involves one side out of several hundreds. Okay, so it's not immediately easy. However, so far the problem has not really been probes, but the biggest problem is that it's very hard to realize this class of Hamiltonian dynamics. So this Kitaev wire that I just told you, it looks very simple, and for theories it is simple, but it's very hard to realize experimentally. Okay? So the reason is the following. Now imagine that we want to have our 1D superconductor. So what we need a large superconductor that provides us the pairing term, and this has to be a p-wave superconductor. And then on the top of that, we want to have a wire that we can do either with an optical lattice or by other means, which confines particle here, okay? And this way we can have tunneling, we can have a chemical potential, and we can have exchange of pairs from the superconductor to the wire. This would be the simplest situation where we can realize the dynamics of this kind. The problem of cold atoms is that p-wave interactions are very lossy. What does it mean? It's because of certain atomic properties. All the atoms which have a small component of the scattering length in the p-wave channel, they also tend to be lost at the same time. So that this means that the system, when you try to realize it, you will lose the particles before you can observe any many-body physics. Okay? So this option is out. You cannot do it. Out. Okay? At least for a moment. I mean, if you can trap and laser cool an atom, and evaporate cool an atom which has a large p-wave scattering length and at the same time is not lossy, then you have solved the problem, but I don't know any. There is a way around it, partial way around it, which is actually motivated by remarkable findings in the concept of condensed matter, and is based on the following very simple intuition. I mean, what is the way of realizing a p-wave superconductor if the only thing I give you is an s-wave superconductor? Okay, s-wave superconductors immediately tell us two things: that there is pairing between two different spin states. So we take a big box, we do BCS theory, and then the other parameter is like k up, a dagger minus k down. In principle, you will say useless. Okay? Because this means that in our wire, I will have two species of atoms and they will realize a dynamics which is very different from the kit I have. Okay? However, there is a way of making a pair of spin species behave very similarly to a single species, and this is by introducing what is called a spin-orbit coupling. Okay? So maybe I write down the Hamiltonian later on. Okay? Spin-orbit coupling is something that realizes for us band structures in combination also to Riemann fields which have this property. I will write the Hamiltonian in a second, but I first want to convey the message. Now, if I have a band structure of this kind, this is a band structure of two spin species, so obviously. Now, what you can do, if you put the chemical potential here, the system behaves essentially like spinless fermions, because there are only two Fermi points. If I'm not very smart and I put the chemical potential here, I have not gained much. Okay? This is just to tell you that if you are smart enough to have a band structure of this type and put a chemical potential here, you can get something. Oh, sorry. That's a magic chemical potential. It's something that looks like spinless. Okay. That's just a very, very raw intuition. Now, how do you get something like this? Well, you have to modify the single particle Hamiltonian of these guys. Tunneling is not sufficient anymore. You have to introduce other terms. You want to have a term that couples the spin to the momentum. So written in the single particle basis, you have the conventional epsilon p. This is just p squared over 2m. Then you want to have something, well, you have your spinor p, and the spinor p is nothing but a p up, a p down, a dagger. Then you want to have something that couples momentum to the spin, and this depends on your community. In condensed matter, this is typically sigma z, because the diagonal has everything in the x basis. For us, it's sigma x. And then in addition to this, in order to have a sensitive splitting here, you also need to have a term which multiplies sigma x. It's a kind of a Zeeman field. Sorry, sigma z, sorry, which has no momentum dependence. Okay? So it is a simple exercise, you can do it atom, a single particle Hamiltonian, you take down the band you write down the band structure as a function. Here there is a coefficient alpha. As a function of this alpha and b, you will find out very easily what are the conditions under which you can realize this kind of band structures. Okay? So how do you realize these two terms in cold atoms? This was simple tunneling, so p squared over 2m. These guys, they are actually coupling two internal states of an atom. Okay? So this sigma x from a cold atom picture, imagine that you have your atoms, and this has two internal states. They can be, for instance, two different sigma states. You want to couple them. Well, the way you do it is by using Raman couplings. Okay? So you have two light beams at different frequencies, and with different Rabi frequencies, omega 1 and omega 2. There is a finite detuning to this transition called delta 1, 2. No, these are the Rabi frequencies. These are not the frequencies. I mean, these two lasers, they will have frequency, let's say, omega 1 and omega 2. Okay? These two levels are two states, for instance, two Zeeman states, for instance. Okay? Let me call it MF. I don't have to specify it. Actually, don't let me write this, okay? There are two different atomic states. Okay? Typically, they are different Zeeman states. What you do, for bosons, they are not Zeeman states, but for fermions, there are. What you do, you couple them off resonantly to a very high line state in your spectrum. And this state is unstable, so you cannot go too far, too close to resonance. You have to use perturbation theory. Okay, so this means that the effective coupling strength between the two is of order omega 1 times omega 2 over delta 1, 2. However, they don't have to be standing waves. They actually have momentum. Right? This is light. What this means that actually this guy come with a momentum k1 minus k2 r when you apply it. Okay? So this is a way of coupling two states and at the same time giving momentum. Is exactly what a spin orbit coupling does. Something that couples spin, degree of freedom, with orbital degrees of freedom, momentum. You want the spin orbit because otherwise these two minima will be here and there will be no p-wave character of the interaction. Okay, I'm hidden some details under the carpet. Because if you just couple them resonantly without any momentum, they don't behave like a p-wave. I mean, p-wave means that you don't have pairing which is local. If you want a pair which is not local, you have to impart some information, momentum dependent character to the band structure. It's the only way of doing that. Now, a term like sigma z, you can immediately read off simply. Instead of putting these two guys with a frequency that matches the tuning here, you just make this laser slightly detuned, slightly, and this will immediately give you also the B. Okay? Now, for theories, this is easy to do. For experiments, it's very tough. These ideas, they were first put forward to realize spin orbit couplings, this kind, in the early 2000s. But they were realized only much later. I think from 2009 onwards, there have been a set of experiments which have realized the spin orbit, and actually with many other things as well. And this is not just an ingredient which is good for spin orbit coupling. It's also what you typically use, this light matter coupling, if you want to realize external magnetic fields. Like if you want to realize the Hofstadter butterfly model, or Hofstadter Hamiltonian, use similar concepts. Now, the really challenging part is actually now to couple this to the S-wave superconductor, and this has not been done yet, okay, in cold atoms. So this part has been done, the rest not. It's very challenging, but hopefully somebody someday can make it through. I don't know. Well, on the wire there are many groups. I mean, I think the first guys who really did that with fermions, this is Jan Spielmann, JQI, Maryland. The group here at Lens has realized this dynamics, but actually they don't use a two-photon transition. Instead of using two Zeeman states, they actually use a ground state and a metastable electronic state, because they have what is called so-called alkaline earth-like atoms, like ytterbium. And there actually, the advantage is that you can do very strong spin-orbit couplings, very, very strong. And they have seen, for instance, chiral currents, many funky things, but also for them it's not so easy to get the pairing. Who else has done similar experiments? And they continue, with fermions I actually do not know if there are many other more spin-orbit fermions. Yeah, I don't know.
So you're talking about coded experiments?
Yes, I'm talking about coded now experiment, yes.
How does it work? Like you have optical lattice as the wire? Or
Yes, essentially what you do, this is an additional further complication, okay? How do you let atoms sit here and not sit outside? But actually you want the same atom here and outside, so the only thing you really need is a potential barrier, okay? And you want this potential barrier to be tunneled through only if you have pairs. And then you need what is called an RF kick to do that. It's possible to do that. But the point is, on the top of this, you want to have the spin orbit. I mean, this is really the challenging part, because you want to have the right band structure. Now, this is, if you want, the simplest way of trying to do Kitaev, while not being exactly Kitaev. One thing which has emerged in the last few years, and this is my last 4 minutes, are techniques to realize Majorana zero modes, which actually are not based on the paradigm of the Kitaev model, but are based on a different one. This goes under the name of canonical Majorana zero modes. So what is, I mean, as I told you, the challenge to do this stuff in Colliatum is that you need a reservoir. This means that the Hamiltonian that you study is not particle number conserving. However, in cold atom it's actually much easier to do something which is particle number conserving, okay? The point is, if I do particle number conserving, this means that I have a U1 symmetry of charge. The very fundamental ingredient to get Majoranas, which was the parity symmetry, is lost, right? I don't have a Z2 anymore, I have a U1. Now, how can I try to retrieve a Z2 symmetry if I have only a U1 at end? Well, there have been two ways of doing that. The first one is, instead of taking a single line, let us take a ladder. Okay? Now, here we put a single species of fermion on this one and on this one. Now, the ladder, we assume that there's a global U1. However, we can think about having terms in this ladder that do not tunnel a single fermion from one side to the other, but they actually tunnel pairs of fermion from one wire to the other, like this. This is what is called pair tunneling. Yeah? Typically, it's written like this. This is the, for instance, the A wire, and this is the B wire. Now, if I have terms of this kind, I have a new symmetry at end, because the parity of each of these two wires is separately conserved. I have what is called Z2 spin parity. And let me put spin in hyphen. Obviously, you will tell me, hey, you're even more lucky because you have a Z2 here and a Z2 here. But this is actually not true, because I have a global U1. So if I give you the total number of particles, and I give you the parity of one of these wires, the parity of the other is a mute variable. It's not a good quantum number. So you have only a Z2, because if, for instance, if this guy is even, and this guy is odd, the other one has to be odd. And this is, and if this was even, this other guy has to be even. So this is not a quantum number. So you have exactly the symmetry that you have in the Kitaev. And you can even be more provocative and tell me, why don't you try to do mean field theory? Okay? If you do mean field theory, wow. This looks like one wire is doing the Kitaev wire for the other, and vice versa. We know that we cannot take mean field theory seriously, so we don't do it. Okay? And there are other ways of tackling this many-body problem, this two-leg ladder with the pair tunneling. At the beginning, with Christina Krauss et al., and this was in 2013, the problem was studied with bosonization and DMRG, And there have been even now exact solutions in the group of Hans-Peter Büchler and also in the PISA group, Mini et al. And Lang and Büchler. This is in 2015, which have shown that actually these classes of models, despite being number conserving, they actually have Majorana zero modes at the boundary. Okay? And now there is hope that maybe not exactly these models, which are already still very hard, but even simpler models can actually be realized in cold atoms. And this, in my opinion, is at present much more promising than going the Kitaev way, because really we are giving up by a lot of, we are actually taking a lot of theory input because we have to formulate new models and study them. But at the same time, we are able to identify scenarios where there are Majoranas, despite the fact that we give up on this having the super reservoir scenario. Okay, with this, I am done, and I'm happy to take any question. No. I think it's actually something that typically, on your conjecture, I don't know, and I think it will be very tough to prove it. But for instance, like what are called topological insulators, which are topological band structure, which are single particle physics. You can understand them by looking at just the symmetries of the original model. And I will say it's not completely different from characterizing states of matter by just looking at the pattern of broken symmetries. You have to use a different... The tenfold classification, yes. For instance, even for bosons, where you don't, for interacting bosons, where you look at group cohomology, so you go beyond the first group property, this is, in spirit, is different from looking at symmetry breaking. So in principle, dualities, they are not immediately helpful. But why not? I cannot say. For a few examples that I know, they are helpful. But this is a tough conjecture that you're putting forward, yeah? Tell you, it will be a lot of work. Questions? No. Guys, I'm here until 1:20, so maximum over lunch. Thank you.